Hello everyone, what's going on? Welcome back to Vedantu JEE English. My name is Pahul and I am an alumnus of IIT Bombay. If I'm audible and visible, please write you in the chat box, you know the drill. Today we are assembled here to attempt and revise the chapter of alcohols, phenols and ethers. The entire chapter is a bit too long, by the way. It's a vast chapter. So in today's session, in the next 1.5 to 2 hours, we're going to try to look at all the important concepts in this chapter that are most likely to turn up in your examinations. And there are a few mechanisms that I would want to revise for you. And there are certain reactions which I would just tell you to revise on your own after the class. Fine? Chalo. So the first thing that we have over here is preparation of alcohols. Starting with how do you prepare alcohols from alkanes, okay? How do you do that from alkanes? There are multiple methods, but these methods are not very common. These are not very common methods. These are maybe used in the industry for very simple alcohols, nothing more than that. So if you take methane and oxidize it, you can use oxygen as well over here, put it in a copper tube at 100 atm 200 degrees Celsius. You realize it's very difficult to create such high pressures, right? So if you do these reaction conditions, you'll get methanol. Another very important way of creation of ethanol, which was asked in JEE last year, is this one. You take water gas. Can anyone tell me what's water gas? Water gas is a combination of carbon monoxide and water. And when you treat it, when you give it some energy in the presence of a catalyst like cobalt or molybdenum, when you put it in the presence of a catalyst, this can also give rise to methanol. So this is a procedure that's mentioned in the NCERT as well, and this is the industrial method of preparation of methanol. Fine. You can take a 3-degree alkane like this, which has only one hydrogen on this particular carbon, treat it with a suitable oxidizing agent. For example, we've taken alkaline KMnO4 over here, which is a decent oxidizing agent. Acidic KMnO4 is far more stronger an oxidizing agent compared to alkaline KMnO4. So alkaline KMnO4 is not very strong, and therefore it chooses this particular hydrogen, converts it to an OH group. So you get a 3-degree alcohol over here, but again this method is not very widely used. Now what's important for us over here is this part. This is the most important part for us. How do we prepare alcohols from alkenes? And a lot of questions will be asked in your examinations from this particular part. Alright. So first method is acid catalyzed hydration, second method is oxymercuration-demercuration, and the third method is hydroboration-oxidation. Let's quickly revise these three methods of preparation of alcohols from alkenes. Before we do that, let me tell all of you that if you want to practice questions daily, if you want to take weekly tests, all India level tests, then what you have to do is just follow the links in the description box down below. We have free test series and free Vedantu daily practice problems available for all of you. So your daily practice is also taken care of, and you can also give an all India level test series to check what's your rank and see whether your preparation is going well or not, right? So test series and also the daily practice problems, links in the description box. Fine. Now coming back to alkenes going towards alcohols. Yeah. So let's take any alkene like this, whatever, and the first method that we'll use is our acid catalyzed hydration. Simply put, H positive in H2O. What will happen in this particular case is, I'm quickly revising it for you guys, that this pi bond will get polarized and it will capture the proton. And what you get in the first position is a carbocation. Now if the substrate is as such that the carbocation can rearrange, it will rearrange. Over here rearrangement is not necessary, it's already a 2-degree carbocation, it can't become stabler. So then your water molecule adds to it, you remove the extra proton, and then finally what you have is a 2-degree alcohol in this particular case. So acid catalyzed hydration of alkenes is a carbocation driven mechanism. You get the OH group on the more substituted side. Yeah, this is the less substituted side of the alkene, this is the more substituted side, so you will get your OH group associated at that particular point. Fine, pretty much. Now people, this is the simplest method. The next method that we have to think about is oxymercuration-demercuration. The next method is a little more interesting. So what we use for oxymercuration-demercuration, it happens in 2 different steps, by the way. In the first step, we put HgOAc whole twice. What is OAc? It's the acetate ion. C double bond O, CH3 with this O negative on top. Acetate ion is associated with mercury twice. So this thing can actually break apart into Hg positive OAc plus OAc negative. So one acetate ion can go away. This is what's left behind. It has a positive character. And now this positive character, this positive charge tries to react with these pi electrons. Fine. So these are the pi electrons. The mercury with the positive charge comes close to it and tries to attract these electrons. And once that is done, what gets formed is something very interesting. Something like this is formed. You remember the bromonium ion that we discussed in the previous class? Yeah, when we were doing the revision of anti-addition of bromine onto a double bond. So something similar gets formed over here, right? Now what can happen is if you add some water to it, this part will attack on the more substituted side. Please keep in mind that the OH group attacks the more substituted side over here. Now you must be wondering, sir, why does it attack the more substituted side? The way to imagine it is very simple. Instead of the cyclic system over there, imagine something like this. If mercury were to go on one side, the other side would get a positive charge. Yeah. Imagine this double bond gets polarized towards the inside, negative charge over here, attracts the positive, makes a single bond with the mercury. Yeah. If this was happening, the carbocation would be on the outside, less stable carbocation. On the other hand, if we were to make this, then the carbocation would be on the inner carbon. Yeah. If you polarize this double bond towards the outside and then capture the mercury, do you see? So this is bad, this is good. This one can be thought of like this. Actually exists in a cyclic fashion, but if you have to think about the H2O's attack, which carbon is more positive in character? This carbon is more positive in character. Fine. So after the attack happens on the more substituted carbon, what you get is something that looks like this. You will have an OH group over here and you have your HgOAc over there. Fine. Now the thing is, what you have to do is you have to take this away. You have to take the HgOAc away. So what you do now is you put NaBH4, which is a hydride ion providing agent. It's a reducing agent. So what this NaBH4 does essentially is it provides you with an H negative, which goes and acts over here and removes the mercury. So the first step was oxymercuration and the second step is removing the mercury, that is demercuration. So ultimately what you remain with is this. Or I can draw it like this. Fine. So once again, the OH group has gone on the more substituted side. That is fine. But the interesting thing about this mechanism is that there was no carbocation involved. No carbocation rearrangement over here. Fine. Harithanam, so the thing is that lithium aluminium hydride is a little more reactive. It might cause side reactions which we don't want. NaBH4 is perfect for this. You can use LiLH4 if you want to, but this is what's generally used in the reaction. Great. Oxymercuration-demercuration. And finally, we have our last method, which is hydroboration-oxidation. So what we use over here is BH3, and this BH3, to stabilize it, as you know, BH3, boron, is an incomplete octet species. So boron over there needs some electrons. It is a Lewis acid. So how it preferably exists is with something called THF. What is THF? THF is tetrahydrofuran. And people who want to revise this class later, I hope you are taking notes. Yes? Chalo. So this is tetrahydrofuran. What does it look like? This particular structure is known as tetrahydrofuran. It's essentially a cyclic ether. And the cyclic ether's oxygen can make a coordinate bond with BH3 to make this happy, because it's a Lewis acid. Fine. Now, how BH3 reacts with this alkene is very interesting. What you have to do is you have to make it like this. Alright, understood? You see, notice the pattern over here. So the boron associates itself with the outer carbon and the hydrogen associates itself with the inner carbon. And what you get over here is something like this. Yeah. The hydrogen goes over here. Now since we are making bond line formulae, we do not need to write hydrogen. So I'm going to erase that. Great. So we have the BH2 getting associated on the outside. Now this particular thing that is formed, people, this particular thing that is formed, I'm going to write it in a different manner. I'm going to write it like this. RBH2, this entire alkyl chain, I have just written it as R. Now what about the alkyl BH2? What about the RBH2? This thing will again react with the substrate. You take the substrate, again react it. So what you will write now is something like this. And then again this reaction happens. This associates here, this associates here. What you will get is something that looks like this. Do you realize this R and this R are exactly the same? So what I can write over here is simply Br2H. So one by one, what we are doing is we are replacing all the hydrogens on the boron with the alkyl group that is there. Fine. So eventually what will happen? This will turn into a Br3. Perfect. And now what does that Br3 look like? Let's draw that over here. And how many carbons are there? 4. This is what it looks like at the end. Now what we need to do is we need to replace this boron with OH groups. At the end of the day, we want to create an alcohol, right? So how we do that is we react it with H2O2. Okay. What does H2O2 look like? It is basically an OH group bonded with an OH group. Make it over here something like this. OH group bonded with an OH group. So this side bonds to this carbon, this side bonds to boron. You do the same thing here and here and here 3 times. Fine. When you do that 3 times, what will happen ultimately is you will form 3 molecules of BOH whole thrice. Can you guys tell me the name for this particular molecule? It's a very common, very standard molecule that's asked quite a lot in inorganic chemistry. And then the other thing that will get formed is what we actually wanted are 3 molecules of the alcohol. Yes. Did you notice what's happened over here? The outside carbon has the alcohol now. This is known as an anti-Markovnikov addition. Less substituted carbon is substituted with the OH group. Alright? Understood? Can you tell me the name of this particular compound? This is what? This is your boric acid. Fine? Perfect. So we revised 3 different ways of creating alcohols from alkenes. Badhiya. Very nice. Now the next thing that I want to ask you is, if I take this as the substrate, and I do those 3 reactions with it, what will the products look like? Will they be the same? First thing that I'm doing is your acid catalyzed hydration. Second thing I'm doing is oxymercuration-demercuration. And the third thing that I'm doing is your hydroboration-oxidation. Just write THF-BH3 and then you put H2O2. Yeah, over here also you can write HgOSC whole twice, and in the second step you can write NaBH4. So now in these 3 steps, this is the alkene. Are you going to get the same result? No. In the first case, what will happen is you will form a carbocation, and the carbocation is susceptible to rearrangement. This is the carbocation that will get formed. Can this rearrange? Definitely it can rearrange. It's gonna... Acha, you tell me. When the rearrangement will happen, obviously it wants to go towards the inside. Will that be a hydride shift or a methyl shift? Tell me. Now when the carbocation rearranges, will that be a hydride shift or a methyl shift? You guys have to tell me in the chat box. Shifa is saying my inorganic and organic strong, physical is weak. You should read the NCERT and solve NCERT questions for physical chemistry. That will definitely help you. Okay. Chalo batao. What shift will happen over here? Okay, very nice. Haritanam and Arvinta and Black Caps have fallen for the trap that I set. So has David. All of you saying methyl shifts have fallen for the silly mistake that you will do in the examination, and that's why I want to take this question separately. There's a bond line formula. This carbon, it has only 3 bonds right now. There is a hydrogen which is hidden. We just don't draw it because it's a bond line formula. And this is precisely the kind of silly mistake that you will do in the examination. That's why I chose to do this in the class. Anyway, so this is going to move towards this side. 1, 2, hydride shift, not methyl. Please don't make that mistake in the examination, alright? And once the hydride shift is done, this converts itself into a 3-degree carbocation. Perfect. And now the 3-degree carbocation can undergo elimination. Sorry, not elimination. It can get attacked by the water molecule, and your alcohol will be formed on this particular carbon. Yes, this is where your alcohol will get formed. In the oxymercuration-demercuration case, you will form the more substituted alcohol, but the carbocation rearrangement won't happen there. There is no carbocation in this particular mechanism. So what's the product? Simply this one. And finally, in hydroboration-oxidation, what's the mechanism? You saw the mechanism, which will give you the alcohol on the outer carbon. Markovnikov product, anti-Markovnikov product, Markovnikov product after carbocation rearrangement. That's why we have 3 different methods of preparation of alcohols starting from alkenes. Nice, right? Perfect. Let's move forward. Now comes the formation of diols. So to form diols, there are essentially two different methods. What are those two different methods? One is syn addition and the other is anti-addition. Essentially what that means is that if you have an alkene, if you add both the oxygens from the same side, that is syn addition. If you add both the oxygens from the opposite side, that is anti-addition. Yeah. Now for syn addition, you can use reagents like KMnO4, you can use reagents like OSO4 or lead tetraacetate. In all of these molecules, there is a similar structure. Yeah, this is the permanganate molecule. OSO4 will look very similar, osmium with 4 oxygens around it. Lead tetraacetate will look very similar, lead with 4 oxygens around it and then the acetates associated with them. So when these approach alkenes, they will approach alkenes from the same side. Yeah, the two alcohols, the two oxygens will approach the alkene from the same side. So these give you syn addition, and then the other mechanism is when we use peroxy acids. What do peroxy acids look like? They look something like this. There is an extra oxygen over here. Alright, there is an extra oxygen over here. So what can happen is when this oxygen, you can say, approaches the alkene, it approaches from one side. Okay, when this happens, the first thing that gets formed is a cyclic ether. One of the oxygens from this goes and sits with the alkene. Fine, this gets formed, then you attack it with another oxygen. So the first oxygen comes from the top side, the other oxygen comes from the bottom. That's why this is an anti-addition. Fine. So two different methods of creation of diols. Diols means two OH groups. Something like this. What kind of diols are these? These are essentially vicinal diols. Vicinal diols. Great. So these are the methods. Please make sure you remember the reagents. Life will be good if you do that. Okay. Just gonna show you a few peroxy acids that can be used for this process. Peroxyacetic acid, trifluoroperacetic acid, metachloroperbenzoic acid. This is very common. Metachloroperbenzoic acid can also be written as MCPBA. So since this is easy to write in examinations, this is it's very common for this to be used in your questions because it's easy to write for whoever is typing the examination. Cool. So don't forget what these are. Peracetic acid or peroxyacetic acid, this is what it looks like, what we had made. Trifluoroperacetic acid, metachloroperbenzoic acid. Cool. Let's move ahead. Next phase is preparation reactions from alkyl halides. Everyone knows by now. You've revised SN1, SN2, E1, E2, E1CB with me. So SN2 reactions can be used to prepare alcohols starting from alkyl halides. So you take any alkyl halide, react it with KOH or NaOH. Depending on the alkyl halide, if it's 1 degree, 2 degree, 3 degree, you can have SN1 reaction or SN2 reaction. Cool. Moist Ag2O. What does moist Ag2O do? Moist Ag2O creates AgOH. And the OH over here can be used to attack the alkyl halide. So don't get confused when you see moist Ag2O, it can give you OH negative. So if you put heat over here, if anyone puts moist Ag2O and heat, the OH negative will act as a base. As I've told you already that heat favors elimination reactions. Fine. So moist Ag2O can also be used for elimination. Please keep that in your mind. Hartanam C. Ag2O plus H2O, this is what? Moisture. So when these two combine, it gives you Ag positive, OH negative. And this is where you get your nucleophile or base from. Tarun bro, thank you. MS, that's very nice, bro. चलो ये करते हैं. How do you prepare alcohol starting from aldehydes and ketones? You reduce them. There are multiple methods of reducing aldehydes and ketones, one of which is simple catalytic hydrogenation. Nickel, palladium, platinum, you take hydrogen over here, hydrogen adds to the aldehyde or ketone from the same side, syn addition, and that gives you a racemic mixture of alcohols. Why a racemic mixture? Because hydrogen can add from here, hydrogen can also add from here, right? So both sides hydrogen addition is possible. That's why you get a racemic mixture over here if the starting ketone has two different alkyl groups on it. Perfect. So this is one way. You can do catalytic hydrogenation on aldehydes and ketones to form alcohols. Another way of reduction is by using hydride ion providing reagents, LiAlH4 and NaBH4. So what these do is they essentially provide you with H negative, and that H negative can attack the carbonyl carbon as is shown over here, and then that thing gets converted into an alcohol. Simple. Methodology is very simple and it's commonly asked in your JEE examinations as well. Fine. Now, this is a very important table, extremely important. LiLH4 and NaBH4 both can react with aldehydes, ketones, acyl chlorides and anhydrides. All of these are reactive enough to react with both LiLH4 and NaBH4. Okay? But the difference in these two comes when we are talking about acids, esters, amides and alkenes. LiAlH4 is a strong hydride ion providing reagent. Why so? Because aluminium and hydrogen are different in size. Aluminium is bigger, hydrogen is smaller, so their bonding is not very strong. So the hydride ion is readily available over there. LiLH4 is more reactive. NaBH4's boron and hydrogen have relatively similar sizes. When you compare it to aluminium, boron is smaller, so hydrogen and boron bond better together. They form better covalent bonds, and therefore sodium borohydride is not as reactive. So LiLH4 can react with all of these. All acid derivatives can react with LiLH4, but NaBH4 cannot react with acids or esters or amides. And generally alkenes do not react with either. So this is the part of the table that you have to keep in your mind. Okay. So whatever is this table, etc., I will share this with you in the Telegram channel, link in the description box down below. But I would still suggest you to write things down if you are revising, making revision notes. This will help you later as well, especially for the second attempt. Great. So what will happen over here? There is this simple acetaldehyde and you've taken LiAlD4. So this will provide a deuterium anion that will go attack over here. Oxygen captures the negative charge. The first thing that gets formed over here is something like this. This O negative is now quenched by the solvent you add. The first thing is attack of the hydride or the deuteride ion, and the second thing that happens over there is you put a solvent later. You let this reaction happen. Once this is done, then you add a solvent. Now that you added H2O, this will provide you protons which can combine with the O negative, and you will finally get your alcohol. Simple. No problems over here, I hope. So now people, this is also very simple. First you put the hydride ion over here. Second thing, now the solvent does not have H positive. The solvent has D positive now. So the oxygen over here will capture a D instead of a hydrogen. That's the interesting thing about these two questions. On the left hand side, you have a ketone. On the right hand side, you have an ester. Yes. So if I react this with LiAlH4, both of these will react, isn't it? But if I react this particular substrate with NaBH4, then what's going to happen? NaBH4 will react with the ketone, but not with the ester. Fine. So LiLH4 can reduce both. NaBH4 will reduce only the ketone part, not the ester part. Cool. Chalo. This particular case is very important. This is the most important part, I think, of this particular part of this chapter. LiLH4 versus NaBH4. So the thing is, over here, the starting material is known as, does anyone know the name of the starting material? This is known as cinnamaldehyde. Cinnamaldehyde. The name comes from cinnamon. You know what cinnamon is, right? Dalchini. Is what it's called in Hindi. I don't know what it's called in your native language. Now people, the interesting thing is that NaBH4 does a standard reaction. NaBH4's hydride ion that comes from here will simply go attack the aldehyde part. So when NaBH4 reacts with this cinnamaldehyde, you get the standard expected product. Fine, the aldehyde is simply reduced to an alcohol. But when LiAlH4 reacts with cinnamaldehyde, LiLH4 is also written as LAH, don't get confused. The hydride ion from LiLH4 is extremely reactive, so it also ends up reacting with the double bond over there. Instead of a 1-2 addition, it does a 1-2-3-4 addition. So it comes over here, pushes this pi bond. This pi bond is also pushed. So the first thing that you form is something that looks like this. And your hydride adds over here. This is the hydride that you added. Fine. This particular thing, I'm sure you realize that this is sort of like an enol form. Yes. Do you see that this is an enol form? This can tautomerize, right? So another hydride ion essentially can come and attack over here now, and eventually what you form is something that looks like this. Hydride was added over here initially. I won't draw it because it's a bond line formula. But the point is that in the case of cinnamaldehyde, specifically in the case of cinnamaldehyde, LiAlH4 will reduce the double bond as well. And you will get a saturated alcohol at the end of it. So since this is sort of an exception, that's why it's quite likely that it will turn up in your examination. Alright. Very nice. Shall we move forward? Okay. Cool. This is what cinnamaldehyde looks like. I didn't realize that the pH is missing from here. Okay. I didn't realize the pH is missing from here. Now I did. So this is what cinnamaldehyde looks like. Fine. So in the case of cinnamaldehyde, please look at the structure carefully. The pH was missing in the previous page. I didn't realize that it was a misprint. So cinnamaldehyde, LiLH4, NaBH4. Double bond is also reduced over here. Over here the double bond is not reduced, only the aldehyde bit is reduced. Very nice. All good, people? I don't know why the attendance is lesser today. Do you have any other sessions or something? Achha, by the way, just a review that you guys should share with me. Are these revision sessions of any use for you, or should I simply do those previous year sessions where I do questions and then while solving questions I revise whatever theory is behind those questions? So you tell me what's better, and I would prioritize taking those kind of sessions. If you get bored looking at just theory, then better solve more questions, right? So let me know, whatever you prefer. Now when we come to reactions of alcohols, we've seen the ways of preparation of alcohols, perfect. Now when we want to do reactions of alcohols, there are two ways in which alcohols can react. Alcohol can act as an acid by simply removing its proton from the oxygen. Just the proton can go away. O negative, H positive, great. Simple. It can also act as a base wherein this particular bond can get broken. Yeah. So this particular bond can get broken as OH negative. That is one way of thinking about it, as a base, provides OH negative. Or you can think that it captures a proton. Capturing a proton is also considered as basic character. Fine. Okay, I can see mixed responses in the chat box. Half of you are saying it's useful, half of you are saying you should solve more questions. I'll take a poll later, perhaps in Telegram. That would be a wise way to decide. Chalo. So let's look at some reactions of alcohols. So my dear friends, can you tell me what are these reactions? What are these reactions doing? These reactions are all dehydration reactions. These are all dehydration reactions. And what you do in all of these reactions is you form alkenes. Alright? In all of these reactions you form alkenes. Acid catalyzed dehydration. P2O5, Al2O3. These are dehydrating agents. Very high temperatures we take. Thorium oxide, POCl3, all of these are dehydrating agents. And how are these reactions different from each other? That is the interesting part. You can take a screenshot of this page if you want. Acid catalyzed dehydrations happen via carbocation mechanism. Acid catalyzed dehydrations happen via carbocation mechanisms. This is literally the opposite reaction of the first thing that we did today. We did acid catalyzed hydration. This is acid catalyzed dehydration. Hydration is addition, dehydration is dehydration, elimination. Yeah. So dehydration or elimination is always favored by heat. So how does this happen? You can think about it like this. You capture a proton which is provided by the acid. This becomes a good leaving group, it leaves. OH2, good leaving group, it leaves. This is formed. Then this gets rearranged as we did in the question that we solved earlier, and then it can undergo an E1 elimination. So carbocation rearrangement is a distinct possibility in the first case. E1 reaction mechanism, obviously Seytzev product. Seytzev means more substituted alkene. Fine. And then you have Hofmann products. What are Hofmann products? Hofmann products mean less substituted alkenes. For instance, if I take the same substrate and react it with THO2 or POCl3, what would be the product? The oxygen will break towards the outer side. What I mean by that is, this is the product that will get formed. Less substituted alkene. I'll draw it again so that it's brilliant. This board is a little messy, but yeah, Hofmann product will look something like this towards the outside. Zaitsev products will look like this towards the inside. What was the starting material? Starting material was this. Wait, starting material was this one. Got it? So these two give you E2 mechanism. These two give you E2 mechanism that looks like E1CB. Do you guys remember the elimination spectrum we had discussed when we were talking about E1CB last week? I think the class happened on Friday itself. Yeah. Remember the elimination spectrum? E2 that looks like E1, E2 that looks like E1CB. So in these two cases, the leaving group leaves first and then the proton is abstracted. In these two cases, the proton is abstracted first and then the leaving group leaves. If you don't remember, please revise that class. You can find that class on the homepage of our channel. You scroll down, you see my face, you'll see the recently streamed live sessions as well. Okay? So just remember this. Let's move on to the next part now. These are all reactions of conversion of alcohols to alkyl halides. So all of these are once again simple substitution reactions. You just need to remember the reagents. Mechanisms are written over there. You use any alkyl halide, use PX3, PX5. These are just halide providing reagents. Then you can use SOCl2. You can use SOCl2 in pyridine, which is also known as Darzon's process. And just have a look at the mechanisms. In the first case, both SN1 and SN2 are possible. If you use PCl3 or PCl5, SN2 is possible. Okay. If you use SOCl2 in the presence of pyridine, then also SN2 will happen. But the interesting thing is, if you do not use pyridine, then SNI happens. What do we mean by SNI? Does anyone tell me what do we mean by SNI? SNI is, it stands for, I'll write the entire name over here, nucleophilic substitution with internal return. This internals I comes over here, SNI. Do you remember what happens in SN2 reactions? There is a Walden inversion that happens, right? Inversion of the stereo center. A backside attack happens. SN2, backside attack happens, so the stereo center can get inverted. It does get inverted. But in the case of SNI, it is essentially the same side attack. SN2 is a backside attack. SNI is essentially the same side attack. So if you start with a stereo, if you start with an optically active carbon over here, you will have retention of configuration. Retention of stereo centers configuration. Now if I start teaching you the entire mechanism in this class, it will take a little too long. This is supposed to be sort of a revision class, yes. So let me share a very nice web page with you guys. I'll share a very nice web page with you guys in the chat box and you guys can check that out. Let me find that web page. There we go. Beautifully written page, by the way. I'll show it to you what it looks like and then I will share the link in the chat box as well. So this is what it looks like. It's from the website called Master Organic Chemistry. Okay. And they've given all the detail about nucleophilic substitution with internal return, SNI. And they've given the mechanism as well, very beautifully. Fine. So you can check this out. I'm going to share this link with you guys in the chat box. And I'm going to pin this as well. So the good thing about this mechanism is that you don't need to remember it as such. Okay. You don't need to remember it. Hey man, just a second. Okay, I'll pin the link in some time. Once you send a few messages, I can pin it. So the thing is that it's not very, it's not very important for you guys to remember the mechanism. I have shared the mechanism with you just for your own curiosity. What you have to remember is that SNI means retention of stereocenters configuration. That's all that means. Okay, cool. So people, please take the screenshot of this chart as well if you want, and then let's move forward. All of these are reactions of oxidation of alcohols. See, what are the reactions that we saw? First, we saw the dehydration, forming alkenes. Then we saw forming alkyl halides. Now we are looking at oxidation. So after oxidizing alcohols, we can either produce aldehydes or ketones or even carboxylic acids. Let me see if I can pin it now. Why can't I pin the message? Did you guys get the message in the chat box? Or is it not visible at all? I don't know. Let me try to send it again. Maybe it doesn't allow sending links. It's visible, right? But for some reason I can't pin the message. I have no idea. I'm going to try and pin it from another page. Just give me one moment. Till the time I pin it, you can look at this. Yeah, now it works. Chalo. So people, there are a bunch of oxidizing agents given over here which are extremely important for us to remember. Questions from these oxidizing agents will definitely be asked in your examination. Somewhere or the other, you will find these oxidizing agents. So, the first two oxidizing agents are extremely strong. Super strong. Alright. This over here is okay-ishly strong. Not very strong, but strong enough. And the remaining oxidizing agents, PCC, PDC, copper and Collins reagent, all of these are mild oxidizing agents, which is written over here. Okay. So if you start with a 1 degree alcohol, that's a 1 degree alcohol, right? So if you start with a 1 degree alcohol, in the first 3 cases, you will get the acid. Over here you get O negative, but then you can put water into and turn it into an acid. Don't worry too much about it. Then you have pyridinium chlorochromate and pyridinium dichromate. These are typically used to convert 1 degree alcohols to aldehydes. Fine. And then finally copper at high temperatures. And then you have Collins reagent, which is again a chromium based reagent. The interesting thing that you should notice over here is when you take chromium or chromium inside water as the solvent, okay, acetone and water. If you take chromium in protic solvents, it acts as a strong oxidizing agent. All of these are chromium plus 6 species. Yes. So if you take chromium plus 6 ion in aqueous solvent or a protic solvent, it acts as a very strong oxidizing agent. But if you take chromium in non-polar media, if you take them in aprotic solvents, then Cr plus 6 is not a very strong oxidizing agent. Keep that in your mind. Haritanam, yes, it is there in your syllabus, I believe. I'm not sure exactly, I might have forgotten it. So do one thing, just download the PDF of the official syllabus from NTA's website. You go to google.com, go search for JEE 2024 official NTA syllabus PDF. And then the first link you'll get is from the NTA website. Just check it out. At the end of it are some extra portions of chemistry that are included. I think K2Cr2O7 is over there, but check it out on your own once. Great. So these were the oxidizing agents. Now, it's pretty obvious that if you use 2-degree alcohols, they will just get converted to ketones. Yeah. So 1-degree alcohols can get converted to aldehydes and acids, but 2-degree alcohols will be converted to ketones. Pretty simple. There are some more selective oxidizing agents as well. This is a point that I've already told you. Yeah, the first 2 points I've already told you. Just this is a selective oxidizing agent. It might get asked in your examination. I'm not sure whether it will. So, ceric ammonium nitrate. What does this cerium look like? You can search for it on Google. It's a huge structure. So, ceric ammonium nitrate, CAN, it does selective oxidation. It brings out mild oxidation of primary alcohols. And it also oxidizes aromatic methyl group into the aldehyde. So it is a mild oxidizing agent. It will convert the primary alcohol into aldehyde, fine. But at the same time, if you have an aromatic methyl group, I'll show you the example. If you have an aromatic methyl group, that also gets converted into the aldehyde. That's the fun thing about ceric ammonium nitrate. So let me show you the example that I have. So if you have ceric ammonium nitrate, obviously the primary alcohol will get oxidized, but at the same time this CH3 will also get converted into the CHO group. Yeah, and that carbon also gets converted into the aldehyde group. Fine, ceric ammonium nitrate. Then we move on to manganese dioxide. This is also a selective oxidant. It's a mild oxidizing agent that selectively oxidizes allylic, benzylic and propargylic alcohols only. You remember allylic and benzylic from our SN1, SN2 class? Yeah. So if you have an allylic alcohol, something like this, or if you have a benzylic alcohol, which is given over here, and this is your propargylic alcohol. Propargylic means you have a triple bond and then you have the OH group on this carbon. These can be oxidized by MnO2 to aldehydes or ketones. Alrighty. So this is a very selective case. There's a slight probability that it will turn up in your examination, but most likely they don't go to these edge cases, especially for JEE main, but you never know. Yeah. So if you have this, yeah, and you put MnO2 in it, the outer OH group, it's neither allylic, propargylic or benzylic. So this will not get oxidized by MnO2, but this particular OH group will get oxidized. So after you oxidize it, what should be the answer? The benzene ring stays the same. This gets converted to the ketone and this OH group remains as it is. MnO2, manganese dioxide. Now people, comes one of my favorite reactions from the alcohols chapter. Pinacol-pinacolone rearrangement. It's a fun reaction mechanism and direct questions can be asked from this. This can also be asked in JEE Advanced. Passage questions can come from this particular reaction in JEE Advanced. Okay, so let's understand what is this Pinacol-pinacolone rearrangement. You have to write it down in case you want to write it down. Chalo, So this type of a structure, this is a vicinal diol. This is called Pinacol. Okay, this is called Pinacol. Some books write it with an E, some books write it just like this. Both spellings are fine. When you put this in acidic conditions and heat it up, obviously you will do some kind of a dehydration. Obviously you will do some kind of a dehydration of alcohol, but the process that happens over here is very interesting, and what gets formed at the end is something that looks like this. Can you see the difference between these two? 2 methyls on left, 2 methyls on right, and at the end you have 3 methyls on one side and only 1 methyl on the other side. One of the oxygens has gone away, dehydration. This particular compound is known as the Pinacolone. Nice, right? How does the mechanism work? It's extremely simple, but it's a lot of fun to understand. So what happens in the first step is, obviously, let's take one of the oxygens. You can take this one or that one, both are fine. You take one of the oxygens and then protonate it. And after protonation, this turns into OH2, which is a good leaving group. So remove the leaving group from the starting material. And the first thing that you will form, we shall write over here, is a carbocation that looks like this. Now people, this might be a 3-degree carbocation, perfect. But if it rearranges, it becomes even more stable. If this carbocation rearranges, it becomes even more stable. So let's try to do that rearrangement and see how it becomes even more stable than a 3-degree carbocation. OH group will obviously not migrate. This particular carbon over here, it doesn't have any protons remaining. There are no protons on that particular carbon. So the only option that you have over here is of a methyl shift. There are 2 methyl groups. Take one of the methyls and shift it over here. So let's write 1, 2 methyl shift. Fine. And once the methyl shift happens, what will this structure look like? The carbocation will move towards the left hand side, the methyl would move towards the right hand side. So the structure that you have after the methyl shift would look something like this. And let's say this is the methyl that has moved. So this side has 3 methyls now, that side has only 1 methyl remaining. What's so special about this particular carbocation? What's so special about this particular carbocation? Think. Yeah, this is what the carbocation looks like basically. It's a positive charge, it's a positive charge that's next to an OH group. My dear friends, what can happen is that the lone pair of oxygen can delocalize in the vacant p orbital on the carbon. This kind of a resonating structure can be made. Oxygen will have a positive charge. People, do you realize that in this structure the carbon has an incomplete octet, but over here all the octets are complete? This resonating structure has only sigma bonds. This resonating structure has one extra bond, that's a pi bond. So when we compare these two resonating structures, this becomes the more stable resonating structure. So if we were to form the hybrid of this particular structure, this is what it will look like. Yeah, there would be a significant positive character on the oxygen and there would be a slight positive character on the carbon as well. This is the hybrid. So because of this delocalization, and after delocalization you get a good resonating hybrid, that is why oxygen prefers, that is why the carbocation prefers to be next to oxygen instead of being a 3-degree carbocation. Okay. This particular resonating structure can also be called an oxonium ion. I'll write it over here. Oxonium ion. Fine. So this is a stable carbocation. Very nice. Now the next thing that can happen is an elimination. Can the elimination happen from this particular side? No, because there are no protons on this side. So the only possible location for an elimination to happen, essentially you want to remove the proton. Yeah, you take a proton from this particular carbon, you throw it away. This bond moves towards the carbon. This is captured by whatever OH negative was released earlier. You can think of it like this. Proton was captured, proton is released. Proton acts like a catalyst. So once this elimination happens, what you will form is this double bond, OH, and then you have your 3 methyls on that side. Do you realize this is the enol form? Enol form will very readily tautomerize and form this. Yeah. The only thing is we've made the flip of this structure. Let me just change this and write it like this so that it looks coherent. There we go. Fine. So this is the reaction mechanism for Pinacol-pinacolone rearrangement. The driving force over here is the formation of the stable carbocation that can delocalize with the lone pair of oxygen. Okay. So this is your standard Pinacol-pinacolone rearrangement. There are some variations of this that can be asked. Let me see if they are here. Yeah, these are some variations of the Pinacol-pinacolone rearrangement. Let's do these quickly. For the first case, what should be the product eventually? Where should we form the carbocation? We can form the carbocation here or we can form the carbocation here. The first carbocation that we form, out of these two, the first carbocation that we can form, over here is just a 3-degree carbocation. Over here it will be a resonance stabilized carbocation. Benzene rings will stabilize this particular carbocation. So in the first step, we'll form this one. In the first step, the carbocation that we'll form is the one that is initially more stable. Now this can undergo, Now this carbocation can undergo the rearrangement to get itself the delocalization with oxygen. So after the rearrangement, you will again have a methyl shift. This is your OH, this is the positive charge, pH, methyl has moved over here, and then you obviously convert this side into the ketone. Cool. Over here, you are creating a carbocation in a slightly different fashion. We all know that bromine reacts with AgNO3. I've told you this in some class in the last week. So bromine and Ag will precipitate, AgBr precipitate gets formed, and this particular carbon will turn into a carbocation. Then the remaining process is the same as the one that we did on the last page. Great. This is also another variation. Yeah. What are we doing over here? We are creating a diazonium salt over here, and then the diazonium salt is a good leaving group. From here, I'll make it for you if you want. So the first step is formation of the diazonium salt. Just a second. This OH group will stay as it is. This will turn into N2 positive, Cl negative. Yeah. And this N2 positive is a good leaving group because when it leaves, it forms nitrogen gas, and nitrogen gas just goes into the atmosphere, leaves the reaction mixture, drives the entire reaction forward. So after this, you can form your typical this carbocation. Yeah, remove the nitrogen gas. So now it's obvious what you're going to do next. Cool. Badhiya. Nice. So this was your Pinacol-pinacolone rearrangement. If you can do a hydride shift, that will happen. If hydride shift is not possible, then methyl shift. So all the examples we saw were of methyl shifts. If there is a phenyl shift that is possible, that can also happen. So let me show you the priority of the shifts that can happen. order of migration of groups, hydride will move the fastest. Yeah. So for example, if you have this type of a system and there's a hydrogen over here, yeah, then you will have a hydride shift. Perfect. If there is a methyl group and there is a benzene ring over here, then out of the methyl and the benzene ring, the benzene will move. Phenyl shift will happen. Alright. If over here, instead of a benzene ring, I had a tert-butyl group. Okay, on this carbon I had 3 more carbons, let's say. So comparing it with a methyl, this is your simple methyl, okay, CH3. And this is your tert-butyl group. The tert-butyl group will migrate. This is just an experimental observation. These hydride shifts, these methyl shifts, the mechanism for these is still not known because they happen very quickly in the reaction. You cannot isolate these shifts. So, what you need to remember is just this, that hydride is better than phenyl is better than methyl, but there are some edge cases where tert-butyl shift is better than your isopropyl shift, is better than your ethyl shift, then better than your methyl shift. So these edge cases are very rare to see in examinations. There was just one JEE advanced question that I've seen till date which had this order. The order was given, by the way, so it was a passage question that had 3 more questions after it. So in the passage they had explained the mechanism for Pinacol-pinacolone and they had given this particular order of migration, and then you had to use that information to solve the further 3 questions. So it was nice. Haritanam is asking, is it important to know the byproducts for all reactions? In organic chemistry, it's not very important to remember the byproducts. Unless your teacher tells you to do so, it's not that important. Perfecto. Let's move ahead. Can we do this question? It revises a lot of reagents. It's a very standard question, nothing too complicated about it, but it revises a lot of reagents for you. Shall we do that? I'll make it a little more interesting. Do it yourself, please. This is a homework. This is a very standard, straightforward question, by the way. I'll give you the hints. PHMgBr, benzene ring, is going to attack the epoxide, acidic conditions opening. So in acidic conditions, listen carefully, okay? In acidic conditions, when you're opening the epoxide, you attack the more substituted side. If the conditions were basic, you would attack the less substituted side. So what you listened to carefully was all wrong. This is the second reaction, this is the first reaction. My bad, listen to me carefully now. Whatever I said earlier, forget about it. So the first step that is given is reaction of pH negative. What is pH negative? Essentially this. This carbon has a negative character. It's associated with the MgBr. So this guy has a negative character. This is sort of a basic carbon, isn't it? So whenever you have a negative charactered species attacking the epoxide, you attack on the less hindered side. Okay, you attack on the less hindered side. If water was given in the first step itself, then this would react with water. So that is why water is given in the second step over here. So negatively charged species attacking the epoxide, outside attack will happen. Okay, great. So then you quench it with water, create the alcohol. Then you do concentrated H2SO4 heat at 443 Kelvin. Dehydration. NBS. N-bromosuccinimide. What does N-bromosuccinimide do? It creates a free radical, provides you with a bromine. Think about it. Then you do aqueous KOH, you do substitution on that bromine. Then you do PCC. After substitution, you would have gotten an alcohol. PCC would oxidize that alcohol to the aldehyde or ketone, whatever. And then after that, you do LiLH4. You do reduction of that carbonyl species, aldehyde or ketone, whatever you form, you do the reduction of that. and then you quench everything to remove the ions. Cool. For those of you who don't know what NBS is, I'll give you the name for it. You have to research on your own and figure it out. Okay? It's called N-bromosuccinimide. There we go. Alright. David is saying, so you look tired. I am not actually tired. It's just that the interaction in the chat box is lesser today. So there's a certain level of monotony that's there in the session, which is not there in the question solving sessions, I know, but since this is a revision kind of session, it's bound to happen. Haritanam, all right, if you say so. See, Dhruv, the thing is that over there you are using I negative, which is a strong nucleophile. Okay, I negative is a strong nucleophile. That proton, HI's proton, will protonate the oxygen that's there in your structure. So once that oxygen is protonated, it becomes a good leaving group. So it can leave either this alkyl chain or the other alkyl chain. I negative being strong, it would do a quick SN2 mechanism. So it would want to attack the smaller alkyl group. Okay, chalo, let's go to the next question. Not the next question, I mean the next reaction. Dawes process. Do you know what this is? This is the formation of phenols. This is the process for formation of phenols. This is very important in the sense that it is asked here and there, just like that. It's a very standard reaction, by the way. Let me see. Yeah. So what you start with is chlorobenzene. Okay? You start with chlorobenzene, and what you do is you react it with NaOH. Now the temperatures are so high in this reaction that the NaOH is actually melted. Sometimes instead of melted, you will find fused NaOH written over here. Okay? So fused NaOH, extremely high temperature, extremely high pressure. Sometimes in examinations, they will give you temperature over here, 600 Kelvin, 300 ATM. Okay? Haritanam is also writing the same in the chat box, 623 Kelvin and 300 ATM. Lots of temperature essentially. 300 Celsius, 300 ATM. You can remember it like this as well. Okay, approximately. And what this does is, this creates phenol. The reaction mechanism that happens over here is your nucleophilic aromatic substitution, SNAR, and the intermediate that forms over here is the benzyne mechanism. Now again, if I start revising SNAR for you right now, it will take 1 to 2 hours just to revise all the details about SNAR. So there are a couple of things that you can do if you want to revise SNAR mechanism. You can simply write SNAR on YouTube and write Pahul Sir next to it. Nucleophilic aromatic substitution Pahul Sir or SNAR Pahul Sir. You will find my video on catalysis by Vedantu, and that's all in English. I've explained this reaction properly. Otherwise, let me just share a couple of more web pages with you. It's the same website, by the way, Master Organic Chemistry. And there are two mechanisms to it. One is your Meisenheimer mechanism, the other is your benzyne mechanism. Let me see if this web page has both of them. Yep, so there are two web pages actually. I'm going to share both of these with you. Haritanam, you will find all of that on Catalysis. On Catalysis by Vedantu, you will have all of my classes for all of the chapters in English. So yeah, there are 11th standard classes over there, 12th standard classes. So people, the links that I've shared right now, one of them is the Meisenheimer mechanism, the other is the Benzene mechanism that happens over here. So you can check those out after the class is done. Vimala, we will do that most likely in the upcoming week. Yeah. If you have time to watch full classes of mine, then you can search on YouTube for Pahul Sir aldehydes ketones. You will see a lot of sessions being shown to you. There are one-shot sessions as well. There are long classes as well from the channel Catalysis by Vedantu. So those are my older videos. You can check those out. They are still relevant for you. If you want to attend a live session with me for revision of aldehydes and ketones, then I'm going to do it probably in the next week. Okay. I think they've kept the session on Tuesday, but you'll know. It will be there in the scheduled live sessions. Fine. So this is Dow's process for formation of phenols. This reaction conditions are what you should keep in your mind. Now let's do another simple reaction. Where is it? Yeah. Williamson's ether synthesis. So what you do in Williamson's ether synthesis is you do a simple SN2 reaction. For a simple SN2 reaction, you take a very small alkyl halide like methyl bromide, because on this you can easily do SN2 reactions. And what you use as the attacking group, this is the leaving group, what you use as the attacking agent is an alkoxide ion. You take any alcohol, let's take phenol over here for this example, okay? And what you do to this phenol is you react it with sodium. So this is like your acids reaction with a metal. Hydrogen gas is evolved and ultimately what you get over here is O negative Na positive. Okay? So if you react any alcohol with sodium, what it will do is it will release the hydrogen gas and O negative and Na positive are getting formed over there. Fine. So now this O negative can act as the attacking group. This leaves typical SN2 reaction. So that is why you need a smaller alkyl halide over here, so that steric hindrance is not present. And ultimately you will get an ether oxygen, which is now bonded to the CH3. This simple mechanism of creating an alkoxide ion and attacking to the simple alkyl halide is known as Williamson's ether synthesis. This is again something that's very commonly asked in examinations. Even in JEE 2023, 2 or 3 questions came from this particular reaction in different shifts, of course. Yeah. Omar is asking, sir, any tips for NEET droppers and to be on track? Just keep solving questions, man. That's the best thing that I can suggest. You got to keep solving questions, and especially in NEET, I don't know about the biology part, I'm not an expert at that of course, but in the chemistry and physics part, the questions are not very difficult. So if you are preparing from a JEE teacher, that NEET chemistry and NEET physics will already feel very easy to you. And once you start solving questions, you will build that speed that is necessary in NEET, because in NEET, it's more about memory based questions and speed rather than logic and calculation. So just keep solving more and more questions, especially previous years. Alright, Williamson's ether synthesis is revised, so is Dow's process. Some reactions of phenols that I have to show you. Some reactions of phenols that I have to show you, and those are here. So my dear friends, this is the electrophilic aromatic substitution of phenol. What you are doing over here is sulfonation. Yeah. So this is a special case when you do sulfonation of phenols. What do you use for sulfonation? You use oleum or concentrated H2SO4 or both. Can you tell me what is oleum in the chat box, please? Let me see whether you remember or not. So if you do that at low temperatures, you will get orthohydroxybenzene sulfonic acid. This is what gets formed. And if you do this at high temperatures, if you provide it enough energy, then the para product is formed. This is the kinetic product. Kinetic means it's formed very fast, very quickly it gets formed. Para product is the more stable product. Why? Because this has less steric hindrance and therefore this needs more energy to be formed. So that is known as the thermodynamic product. Now, Harsh Nikesh is asking, is it necessary to learn all the mechanisms? See, that's why I always recommend that you should follow a certain teacher in organic chemistry, because then the teacher will tell you which reaction mechanisms are important for you and which are not important. For instance, today we saw the Pinacol-pinacolone rearrangement method. Over there the mechanism was important. Yeah. Then we saw the Dawes process. Over there the mechanism is good to know but not very important. Yeah. There was another case that I did today where I said the mechanism is not important. I don't know exactly what question it was, but there are certain places where you don't need to remember the mechanism. Yeah, like the SNI mechanism, SOCl2 attack onto the alcohols. So SNI mechanism is not important for you to remember. You just need to remember the result. So it depends what reaction it is, and the teacher will be able to tell you the best whether you should remember it or not. Perfect. So please keep this in your mind. Let's move ahead. My dear friends, just a second. I need to create, okay, we'll do this in a while. We'll come to this part, but to come to this part, we need to understand something. Do you remember what this reaction is? And we've done this in a question solving class as well. CH3 C double bond O Cl in the presence of AlCl3. What is this reaction? This is your Friedel-Crafts acylation. Yes, Friedel-Crafts acylation. What happens over here is that the chlorine group is removed from here. This turns into an electrophile. Yeah, and then the electrophile can go and react with the benzene ring. Yes, is that okay? Friedel-Crafts acylation, very nice. You will get benzaldehyde. Now the thing is that if I have a phenol over here, Friedel-Crafts reactions are not possible. Friedel-Crafts acylation or Friedel-Crafts alkylation, both these reactions do not work with phenol. Can you guess why? And the hint is that AlCl3 is a Lewis acid. A Lewis acid is something that wants an electron pair. When there is no OH group on the phenol, then AlCl3 approaches this chlorine, says, okay, chlorine, you break your bond and come to me. That happens. But now when there is phenol, AlCl3 has an easier option. Instead of telling someone to break a bond, it will simply go close to the oxygen because oxygen already has two lone pairs on it. And this oxygen can very easily form a coordinate bond with AlCl3. So AlCl3 stops acting as the starting material over here. AlCl3 does not activate this. No reaction is possible. So whenever we want to do alkylation or acylation of phenols, we use different methods. Omar is saying adduct gets formed. Yes. For those of you who don't know what is an adduct, it is just an addition compound. Phenol adds to AlCl3, they just exist as that adduct. Okay. Omar is saying same in aniline. Theoretically, yes. Aniline is although not as, yeah, it happens. You are absolutely correct. Same in aniline because nitrogen's lone pair is also basic. So whenever you have something that can provide lone pairs to Lewis acids, Friedel-Crafts does not happen. Now, what do we do in that case? we use other methods. So how do we alkylate it? Let's try to understand. We will take an alkene and put it in acidic conditions. Whenever we put alkenes in acidic conditions, a small part of the alkene turns into a carbocation. Basically, the proton is captured. Not a very good drawing. The proton is captured on the outer side and a carbocation gets formed over here. Fine. Now this carbocation can act as the electrophile. Yeah. So the carbocation can act as the electrophile, and now the typical electrophilic aromatic substitution can take place. Now you must be wondering, sir, why doesn't it form a bond with oxygen? Why with carbon? Because carbon-carbon bonds are more stable. So even if the oxygen thing gets formed, it is an equilibrium reaction which eventually gets driven to the more stable carbon-carbon bond formation. So you have to provide it enough energy for the reaction to happen. Once you provide energy, carbon-carbon bond formation is more favored over oxygen-carbon bond formation. So this ring alkylation is very common. They will just give you some phenol, they will give you some alkene, they will give you some acid. You need to figure out what carbocation needs to be formed and where will the attack happen. Great. Then, just let me see. Yeah. Oh, there's Kolbe, there's Reimer-Tiemann for salicylic acid, and there is this one that's remaining. So 2-3 reactions are remaining, people. Let's finish those as well. Another 15 minutes or so. Now we have coupling reactions with diazonium salts. How do we create diazonium salts? Do you remember that? Let me revise it for you if you don't remember. To create a diazonium salt, you start with aniline. And on aniline, you do the typical reaction of NaNO2 plus HCl at 0 to 5 degrees Celsius. Essentially, you do this in an ice bath. You take a bucket of ice and then put your test tubes in it, and then you do this reaction. Good morning, Samanyu. Once this happens, you will get your diazonium salt. This is what gets formed. Now this diazonium salt has interesting properties. If you put a lot of heat over here, if you reacted with some nucleophilic species, that nucleophilic species can displace the entire diazonium salt as well. But since this particular carbon is not good for substitution, you can preserve the diazonium salt and react it with something else. How? This is the diazonium salt. This is what the structure is. You have a positive charge over here. This diazonium salt can act as an electrophile. Positively charged species, right? It can act as an electrophile. So what can happen over here is the para position. OH group is ortho-para directing, so let's do the para attack. The para position can attack over here on this particular nitrogen. When this attack happens, this particular pi bond will get polarized towards this nitrogen and its positive charge is gone. Yeah. If this kind of a reaction happens, this is a typical electrophilic aromatic substitution where the electrophile is a diazonium cation. Nice. So, the product that gets formed over here is very interesting. The product that gets formed over here is a long chain OH, which has these double bonds, of course, resonating, N double bond N, and then there is another benzene. My dear friends, do you notice that there is a lot of conjugation that is happening in the system? Can you see all the atoms that are in conjugation with each other? What are the atoms? This oxygen's lone pair, all of these carbons obviously because there are benzene's carbons, this nitrogen's lone pair, this double bond, not the lone pair, sorry, this double bond, all of these carbons, they are all in conjugation. Yeah, essentially this lone pair, all of these p orbitals of carbon, the p orbitals of nitrogen, and again all of these carbons as well. All of these orbitals are in conjugation with each other, extended conjugation. Electrons can delocalize over a lot of space. What ends up happening after this is that this compound, because the electrons can move very easily, even if you shine light at them, they can get excited and come back to ground state easily. So since they can absorb visible light easily, they show you color. That's the small explanation of things. If you want the long explanation, it will take a lot of time. The small explanation is, since the electrons over here are delocalized, they become stable, they can move around. So even if you shine visible light on them, which is low energy, high energy is ultraviolet or gamma radiation. Visible light is low energy. Even if you shine low energy light on it, electrons will capture it and move somewhere. So some light will be captured, some will be reflected. Whatever light is reflected is visible to you as color. These are colored compounds, and that's why these compounds were used as dyes. Some of these are harmful because these can turn carcinogenic in nature. Carcinogenic means causing cancer. So a bunch of azo dyes are now banned. But yeah, that is, sorry, this can be used to color things. Yeah. So you can read about azo dyes on Wikipedia. If you search for azo dyes on Wikipedia, you'll get a nice article. They've given the colors and stuff about different dyes. They've given images. So now if I do the reaction over here, what will happen? You have blocked the para position. The para position doesn't have a proton now, so you can't do a para attack. So instead you will do an ortho attack over here. Yeah, this will form a different type of a compound. The compound will look something like this. Right? Just a different type of a colored compound. So that was your diazo coupling reaction. Now, my dear friends, let's come to Kolbe synthesis. Okay, we still have time. I have to take a class at 8 p.m. actually, so that's why I want to finish all the reactions properly while still being fast, because this is technically a revision class. Kolbe synthesis, what happens over here is very interesting. First step, okay, these are three different steps. First step, you react this with NaOH. So oxygens, I mean, this is what, OH negative, right? So OH negative captures the proton from phenol, because phenols are decently acidic, not very acidic like carboxylic acids, decently acidic. So this is what gets formed first of all. Then in the second step, we reacted with CO2. CO2 basically is a good electrophile. How is it a good electrophile? By carbon has a lot of positive character. 2 double bond O's on carbon. This has a lot of positive character. So what can happen over here is, this lone pair can move here. Essentially, we have to do just an electrophilic aromatic substitution once again. Cool. Just to show you the arrow pushing. And after this, let's form the combined thing. You will get a double bond O at the top. These bonds we haven't touched at all. You get a new bond with carbon. Obviously, if carbon gets attacked by something, one of the bonds has to break, and that will break towards oxygen. So you form an O negative, and one double bond O remains the way it is. Again, what will happen here? Can anyone guess what will happen over here? This particular proton can be eliminated. Yes, this particular proton can be eliminated. So if it's eliminated, you will move the electrons towards the carbon, and the structure that will get formed is something like this. Yeah, I'm showing you the intermediate. Obviously, you would move the negative charge towards oxygen. So what you are forming is a double bond over here. You are regaining the aromaticity like you do with electrophilic aromatic substitution. Since we are starting with phenol over here instead of directly benzene, just some extra arrow pushing is involved. Ultimately, what's getting formed is straightforward. Yeah, O negative, C double bond O, single bond O negative, whatever. Yeah, and once you put water at the end, yeah, once you put water at the end, these get converted into OH groups. Sorry. People, what is this called? Do you know the name of that compound? Please tell me in the chat box as well. So that compound is known as salicylic acid. Salicylic acid. And salicylic acid is a starting point of a lot of useful compounds. What are the compounds that can be formed starting from salicylic acid? Now it has an alcoholic part and an acidic part. Alcohol and acid both in the same molecule. So if you reacted with another alcohol, acid plus alcohol is ester. So another alcohol can react with this particular compound to form an ester over here. Okay? Alcohol will form an ester with the acid part. If you reacted with some acid or acid derivative, then this will attack on the acid and the ester will be formed over here. So, depending on whether you react salicylic acid with alcohol or acid, you will get different kinds of esters. And those esters of salicylic acid are of a huge significance. Let's see those cases. This is an acid derivative. Can you tell me what's the ester that will get formed over here? The acid part will get attacked by the phenol part of salicylic acid. So, this is what we should get. Oxygen, C double bond O, single bond CH3. Forget about this part, acetic acid banke, that will go away. That will go away as acetic acid. And there you have this particular compound. And this particular compound is of extreme significance. Why so? What is this compound, people? Haritanan has already mentioned what it is. Yeah. Aspirin. Alright, acetyl salicylic acid, also known as aspirin. Aspirin is a painkiller. More details can be given by these two bio students that are there in the chat box. Nice. Salicylic acid plus methanol. So where will this form an ester? It will form an ester over here. Yes. Methyl salicylate, methyl, methyl, whatever you want to call it. Oil of wintergreen. It's just something that smells like minty. Yeah, you have that eucalyptus oil kind of smell in this. Like your Vicks, yeah, camphor, eucalyptus oil, these all smell very similar. Great, you understood salicylic acid. Phenyl salicylate, salol. If you reacted with another phenol, this forms salicylic acid and phenol, so it is called salol. Simple reactions, nothing to worry about over here. And finally, the last reaction of the day is Reimer-Tiemann reaction. After this reaction, there is one more reaction that I will tell you to revise on your own. So people, what happens over here is, yeah, something very similar happens. You take a lot of NaOH, you take chloroform and you take phenol. So when base reacts with phenol, obviously what gets formed over here is this. But when base reacts with CHCl3, can you tell me what happens? CHCl3 plus OH negative plus Na positive. what happens over here is very interesting. OH negative captures the proton and a chlorine is attracted towards the sodium, ultimately giving you something like this. Obviously, water and NaCl can be found at the side, forget about them. The interesting thing that comes out of here is CCl2 with these two electrons that have not reacted. These two electrons can exist as paired electrons, these two can exist as unpaired electrons as well. So do you realize what you've done? You've taken away H positive from this carbon. Yeah, think about it. When H positive is taken away from the carbon, what happens? You will get a carbon ion. This has extra electrons, but now instead of using this electron pair to react, what you do is you take away one more electron pair towards chlorine. So you took away a positive charge and then you took away a negative charge. So ultimately you get a species that has these two unreacted electrons, but this species overall is a neutral species. Alright, so this particular intermediate, it's a reactive intermediate because again the octet for carbon is incomplete, and this particular species is known as dichlorocarbene. It exists in two forms, it's called a singlet form and a triplet form. Essentially these electrons can exist paired in one orbital or they can exist unpaired in two different orbitals. That part is not in the syllabus, so we won't discuss it right now. You can search more about carbene on Wikipedia and read about it if you want. But this is essentially a neutral intermediate. Okay, you give electrons to this, again it forms a carbon ion. Keep that in your mind. When you give it electrons, again forms a carbon ion. Cool. So let's do the reaction of this phenol with dichlorocarbene. So essentially in this particular reaction, it's again an electrophilic aromatic substitution, but this dichlorocarbene acts as your electrophile. Okay. Please write this down, then I'll do the reaction mechanism as well. Haritanam, yes, you can revise that. Otherwise, I'll do that again in a Minds chapter. What I wanted you to revise on your own after this particular reaction is FeCl3 test for phenols. That is sort of important for the examination. Let's do the mechanism now. So, you got your O negative and you reacted with your CCl2. Again, push the electrons over here, polarize this bond, attack the CCl2, and what you will get now is something that looks like this. Double bond O. You have a carbon with two chlorines, and then you have a negative charge over here as well. Do you realize that? There is a negative charge over here as well. Why is there a negative charge over here? Because again, you have given electrons to the carbene, so now it turns into a negatively charged species. Now what should we do? Now the process is the same, by the way. Okay. Now the rest of the process is very similar. You remove this proton. You don't remove this proton as of yet. Can anyone tell me what's the rest of the procedure? Can you think? How do we stabilize this negative charge? Sorry. How do we stabilize this negative charge? Can you tell me? I'll tell you the final product of this. Okay. Final product is basically this. I'll give you the hints. You have to figure it out on your own. This is what you have to do at the end. Okay. And when this is formed, the OH and OH will, there is a dehydration that happens over here. This will turn into a C double bond O. But how do I reach here? Can you tell me? You do not remove this proton entirely, you shift it to this carbon. Okay. This proton that we used to remove in electrophilic aromatic substitution, you simply capture the proton by this carbon and give the negative charge to this carbon. Just do that, let's see what happens. Just a second. This CHCl Cl. There is a negative charge over here and there is a double bond over here. Now obviously this negative charge can delocalize and give you the O negative. Yeah. So negative charge forms a pi bond here and this turns into an O negative. Now all you have to do is replace the chlorines with OH groups. How do you do that? OH replaces chlorine, substitution reactions twice. That automatically will lose water because as I told you last time, hydrates are unstable, yes? Hydrates are unstable. We did it in a question solving class if you remember. So essentially this will lose water and turn into this particular compound. Salicylaldehyde. Okay, you can call it salicylic aldehyde, you can call it salicylaldehyde, you can call it salicylaldehyde. All names are fine. Salicylaldehyde is formed at the end of Reimer-Tiemann reactions. Perfect. Chalo ji. So my dear friends, if you want to read more about carbenes, it's written over here. You can take a screenshot of this. Otherwise, I'll tell you, this is an excerpt that I've taken from the Wikipedia page. So you can simply go to the Wikipedia page and read it on your own. What you have to do after this are a couple of more things. Okay. These are some reactions that you have to revise on your own. First thing is FeCl3 test for phenols. Okay, this is something that you can revise on your own. There's another test called NaHCO3 test for phenol versus acid. We will anyway cover this in acids chapter, but if you want, you can revise it right now. Okay. There is another test called Lucas test. Very simple tests, by the way. You can simply Google them and in 5 minutes you'll be able to understand what these are. Okay. So FeCl3 test, NaHCO3 test and Lucas test. Let me write the spellings properly. Alright. So just revise these parts and then most of this chapter will be done for you. Badhiya. So people, this is where we will wrap up today's class. I have to take another session on Vedantu JEE Hindi channel at 8 p.m. Haritanam, yes, you can do that from the NCRT as well. Srimuga is saying, what will happen in the sodium bicarbonate test? See, sodium bicarbonate is essentially something that acts like a weak base. So it will only react with strong acids. Alright. कियारा, हाँ जी आती है हिंदी में, हिंदी में पढ़ाता हूँ मैं. I take classes in Hindi and English both. Alright. Very nice. So people, thank you so much for joining into this class and I will try to share this PDF on Telegram channel with you guys tonight after all of my classes are done. I'll try to share the PDF, although I'm sure whoever has attended this class was able to revise everything from the class itself. But in case someone needs the PDF of whatever the already written text was, I will share it with you later. And the next class on this channel, I think, is on Tuesday, if I'm not wrong. And that is for such a revision of aldehydes and ketones. But I will try to take a poll on Telegram either tomorrow or day after or Saturday or Sunday to see whether you want these revision sessions or shall I simply go for PYQ sessions of organic chemistry. We'll see. Alright. So chalo dosto, thank you so much for joining in. I'm going to see you very soon. Bye bye, take care. Make sure you hit that like button before you go.